Hello back. In the last video, we left off after the discussion of the various pKa's of the amino portion of amino acids, the carboxylic portion of amino acids, the side chains, and some noteworthy, outliers. But now what we're going to do is look at something known as the isoelectric point. And it's best to start with an example to fully, explain what that ultimately means. So let's say that we're looking at glutamic acid, right? We have the amino component right here, the carboxylic acid, and here's the side chain, 2 carbons long, and then second carboxylic acid. So if you look up the values for the pKa's, the pKa of the main carboxylic acid unit is 2.19. The pKa for the amino portion of glutamic acid is 9.67. And the pK of the side chain carboxylic acid is 4.25. All right, and the idea here is that because these different protons have particular pK values associated with them, changing the pH of the solution can also alter what form you have for that specific group. So for instance, in a pH of 0 to 14, based on what we have here, which is 3 pKa's, we have 1, 2, and 3 boundaries that we can go through as we start increasing the pH. So in the case of our molecule here, glutamic acid, the lowest pK value is 2.19. So we will have a boundary, at about that value when the deprotonation of the carboxylic acid group begins to happen. And then if we continue increasing the pH, once we hit a value of about 4.3, 4.2, we're going to start considerably removing the proton of the second carboxylic acid unit. And then it won't be until we reach the pH all the way up to 9.7 that we'll see the protonation of the amino group beginning to happen. Now, as far as the identity of the molecule, the most acidic boundary, the one where we're below the lowest pKa, will have all the carboxylic acids protonated and neutral. At the same time, we will have all the amine groups, all the basic groups for that matter, protonated and positively charged. And it's important to remember that because the best strategy for what I'm about to show you is to always start with the most acidic version of the amino acids and then make our way across. And the reason for that is because when you look at this molecule, you should realize, okay, we have a +1 charge in this molecule overall because of the amino group that's protonated. Now, as we begin increasing the pH, once we cross the pH value equating to the pKa, we will, in essence, start producing significant amounts of the monodeprotonated amino acids, specifically at the carboxylic acid of the regular chain. When that takes place, notice that the charges overall will add up to 0. This will be a neutral molecule. And going beyond a pK of 4.3, going beyond a pH of 4.3 will get us into the next deprotonation, which now will yield a molecule that is negatively charged, 1 minus if we want to be technical. If you continue with the deprotonation past a pH of 9.7, then at that point you'll start deprotonating the amine. But the amine being deprotonated means that you go from being charged, positively charged, to now being neutral. But if you look at the sequence of events, we start with a molecule that has a +1 overall charge, then it's 0, then it's -1, and ends up at -2. So there's always this progression of decreasing the charges by 1 as you increase the pH of the solution. Now, among them, as I mentioned already, the molecule in region B is neutral. And because of that, this has a special connotation in biochem because technically speaking, even though you do have charges, having this neutral place allows you to, have certain properties in terms of the, electrical properties, in terms of the even solubility to some degree. So knowing this particular pH value is important. And then to give you full context, if you kind of think about the deprotonations the proper way you ought to be thinking of them, which is to pretty much recall a titration curve, the moment that you reach the first pKa, you've only gone through half of the molecule in terms of the protonation. So you will have half of A and you will have half of B at the first equivalence point. And it's not until you reach the first equivalence point, not the first half equivalence, but the first equivalence point, that you finally will convert all of A into B. So you'll have 100% B at the equivalence point, the first one. As you continue increasing the pH, you will move away from the first equivalence point and you will reach the second half equivalence point, at which half of the molecules of B have been deprotonated. So now you only have half of B at the second half equivalence point. And by the time you get to the second equivalence point, well, you'll have converted all of B into C. Continue that approach and you'll go all the way up to D eventually. But since the neutral molecule falls already within this range, specifically, it falls right after pK1 and technically before pK2, right? And if you look carefully at the titration curve, what you should realize is that as far as the pH scale is concerned, the pH at the equivalence point where you have 100% of the neutral species is nothing more than the average of pK1 and pK2, right? So you will simply just take pK1 and pK2, add them together, and divide them by 2. And that will end up being, in this case, 3.20. But that number is what we call the isoelectric point, and it's abbreviated as PI, because this will be the pH at which the amino acid will be neutral. All right, so just like glutamic acid, you could also encounter the situation where your amino acid has basic units, such as the case of histidine. With histidine, you do have your carboxylic acid with a pK of 1.82, you have your amino group with a pK of 9.17, and then you have histidine with a pK of 6.0. So, as far as determining the situation here, you have 3 pKs, so you have 3 boundaries to go through. So 1, 2, and 3 boundaries. The lowest one is 1.82, the next one is 6, and then the last one is 9.2, roughly speaking. All right, so we start once again from the lowest pH possible, which means that all the carboxylic acids are protonated and neutral, all the basic groups are protonated and positively charged. So what that means is that on boundary A, or region A, we will have the carboxylic acid neutral, we will have the amine group positively charged, and we will have the histidine, the imidazole unit, also protonated and positively charged. So altogether, this molecule has a 2+ charge. So as we increase the pH and we go past the first pK value, we will deprotonate the carboxylic acid. And now all of a sudden we have a negatively charged unit, which altogether brings the value down to +1 for the overall charge. Continue increasing the pH until you hit 6. Now you will deprotonate the imidazole unit. So now you have a neutral molecule. And if you continue increasing the pH past 9.2, you'll deprotonate the amine as well. But at that point, the molecule will have a charge of -1. So the one that's neutral is the one that now resides in region C. And region C, as you can see from the graph, will basically reside, basically right at the third equivalence point, right? So we'll go through, excuse me, yeah, the third equivalence point. So we go through the first equivalence point, then we go past it, we form B, and eventually, we go to C. And, since we're going to be going through 1 and 2 potential deprotonations, right? And that gets us into region C. We have to pay attention now at the second and the third half equivalence points. And since we're looking at that specific pH, the one of the second equivalence point, the pH is going to be approximated by taking the average of the 2 pK values that are sandwiching that pKa. So in essence, you look at the lower boundary and the upper boundary in this box. Those are the pKa's that you should be taking the average of. So in the case of this molecule, histidine, we'll have 6 and 9.17, which averaged out will give you a value of 7.59 for the isoelectric point. All right, so that concludes the, at least for now, the analysis of the isoelectric point. There's going to be one more instance that we bring it back again to kind of look at the full extent of it, and that will be once we talk about oligopeptides. But in the next video, we're first going to concentrate on how to synthesize amino acids. So now it's going to begin to feel a little bit more like organic chemistry. But anyway, we're going to save that topic for the next video. So catch you then. Bye-bye.